Well, today we are going to talk about my final project regarding cancer detection by convolutional neural network. As we all know, cancer detection is currently performed by pathologists. They manually review the digitalized images of glass slides which contain tissue specimens. These digitalized images are usually large gigapixel images, so they are at high resolution. So it is hard to scan whole images manually. The current detection process is label-intensive and error-prone. So we need some more rapid, cheaper, and precise method for preliminary diagnosis and reduce the workload of pathologists. So our objective of the project is to develop a deep learning-based tool to automatically detect and localize tumors in gigapixel images. In this study, we have one slide image with 7 magnification levels. At each level, we have one input slide and one mask image. The input slide is a whole slide image of lymph node, and the mask image contains the true diagnosis of metastases. We will use one of the downsampled version of the original image to prepare our dataset. We extracted paired patches from the input slide and mask. Paired patches are in the same location in slide and mask images, as we can see in the picture. So we will get multiple patches for training and test. Those patches contain a feature of tissue and the corresponding diagnosis. We will train our model on those patches and make prediction on test image to obtain the probability of metastasis. Based on the predicted probability, we can generate a heat map like this. So let's take a look at the project pipeline. As shown in the slide, there are 5 steps. We will start with detecting region of interest, which is the area of tissue. So why do we want to find the region of interest first? Because the image is very large, finding the tissue area will reduce the computation time. So we firstly convert the RGB images into grayscale images. So those pixels with great intensity, less than 0.8, will be identified as non-tissue area. So when we extract patches, if 5% of the patch contains tissue, we will save the patch into our dataset. Otherwise, we won't consider it for training. So like in this image, the yellow region are non-tissue area, while the blue region is of interest. So after finding the region of interest, we extracted our samples from the slide image and extracted corresponding annotations from the mask image. The patch size would be 299 multiplied 299, and the positive patches represent tumors. The negative patches represent normal tissue. Then we divided whole datasets into training, validation, and test datasets. We use training and validation sets to train our convolutional model. As we said here, we used a pre-trained model, which is Inception v3, and add some dense layers. So after evaluating the performance of the model, we created a new test dataset on the same image. We slide out the windows one step to extract new bunches of patches. Then we predicted the probability of containing tumors for each patch and build a heat map. Now we move to look at some essential steps. So for pre-processing steps, we use images at level 2 to create samples. And we use the function in OpenSlide to extract patches, both in slide image and the mask image. The patch size matches the input side of inception V3. So if we change the pre-trained model, we need to change the patch size at the same time. I also created an array with the same patch size to represent the tissue area. So how can we tell which patch is positive and which one is negative? Here we can see if any pixels in the mask patch are 1 and at least 5% pixels in the tissue patch are 1, then we save the slide patch into a positive directory. If none of the pixels in the mask patch are 1, then we save it to negative directory. So finally, we have 71 positive patches and 983 negative patches. So apparently the dataset is imbalanced. To make sure that our training set is balanced, so we selected 71 patches from both positive and negative directory separately. Look at the codes on left. We shuffle the dataset in each directory and copy the first 50 patches into a training folder, and the next 10 patches to validation folder, and the last 11 to test folder. So in total, we have like 100 patches for training, 20 for validation, and 22 for test. So when we are doing feature extraction, we also conducted data augmentation. So we only conducted data augmentation on our training set. So we do like rotation, horizontal flip, and brightness change. So as we mentioned before, we extended the inception V3 base by adding some dense layer on top. So we add some dropout layers to prevent overfitting and use sigmoid as the activation function for the last layer. Here is our optimizer and the learning rate. So before we compile and train the model, we freeze the convolutional base. So as the result, we can see from the plot, the model reached a validation accuracy about 80% to 90%. It is a little bit unstable, and the training accuracy is above 90%. So maybe the unstable performance is due to the small size of my training and validation sets. And also, as a result of the model evaluation, the test accuracy is about 91%. So to better evaluate my model performance, we use the F1 score as the evaluation metrics. In our case of cancer detection, false negatives are probably worse than false positives. For example, patients with false positive diagnosis could take detailed screening to clarify, while patients with false negatives would be sent home without knowing the potential risks. So classification accuracy is not enough here. We need to take into consideration about the false negatives. So here we have the formula for F1 score in our model. And we can see that the F1 score balances the precision and the recall. We can see that we have pretty high F1 score for our model. So apart from the model we just mentioned, I also conducted some experiments on model without augmentation. It is much faster, but it has the problem of overfitting. And also considering that my dataset differs a lot from the dataset used for training inception V3, so I also fine-tune the model to see the accuracy. I only fine-tune the top layers in the convolutional base, but the accuracy and F1 score are even lower. Also, since our dataset is very small, I try to use more slide images to train the model and improve the accuracy. So I mounted my Google Drive on the virtual machine and connected to Colab. I included like 8 slide images in our samples and read images at level 3. So in total, finally we got 498 positive patches and 4572 negative patches. But however, it turned out that the accuracy is not as good as we expected before, and the F1 score is only 52%. So after all the model training process, now we can apply the convolutional model on a test image to output a heat map. So to get a new test dataset, we slide one step on level 2 images to generate new patches for the same image. Then we predict on the new datasets and obtain a vector of probabilities. We match the predicted results to the corresponding patches and combine all the patches with probability values into a heat map. Here is the heat map we got. So the red regions are more likely to have tumors than the others. Okay, well, that's all for my project, and thank you all for listening.